A POMDP is the acronym for a partially observable Markov decision process. It's a single-agent framework for describing a broad, maybe universal, class of problems that involve agents working under uncertainty of the state and the impacts their actions have on the state. A DEC POMDP, or Decentralized POMDP, is a generalization which captures multi-agent coordinated decision-making. This is Data Skeptic Consensus, and the 25th installment in our series about how multi-agent systems achieve collective decision-making. Today on the show, I speak with Mikko Lauri about his contributions to the field, which make these otherwise powerful but intractable solution frameworks practical through the use of heuristics.
So my name is Mikko Lauri, and I'm a postdoctoral researcher at the University of Hamburg in Germany. My research interests focus on multi-agent systems, and in particular the aspect of decision-making in those systems. So I'm interested in particular in information gathering tasks. So you could think of like a team of robots trying to find out something about the world and doing this in a collaborative fashion. So that's the kind of task that I'm interested in, and especially the decision-making aspect of that.
A while ago, when there were some Mars missions being planned, I think we ended up sending Curiosity and I forget the other one, maybe Opportunity. There was some discussion of, hey, maybe instead of sending 2 rovers that cost a lot, like, $1 million, we should send 1 million rovers that cost $1 or something like this. Didn't happen, but is that the kind of case that would be interesting to a researcher like you?
So my interests are maybe more so on the side of the 2-agent case. So at least that's the situation for now due to the computational complexity of the problems that I'm involved in. There are certain practical limitations that usually mean that more than a handful of agents is still beyond the reach of current state-of-the-art methods.
Yeah, the fact that your work has heuristics involved is what actually at first attracted me to it. So maybe we should talk about the elephant in the room, computational complexity. What would it be like to try and solve one of these problems in a sort of rigorous, complete, not necessarily brute force, but an exacting method?
Maybe conceptually it's quite instructive to think about how you could actually solve this kind of problems in this brute force manner. What you typically have is that you have your set of agents. Then each of the agents has some possible actions that they can take. And as a result of taking some of these actions, they're going to perceive then some observations from the world or the environment. You can kind of see that when you have multiple agents acting simultaneously, of course, there's an exponential number of possible combinations of actions that the agents could take. So this is already an indication that it's going to be quite complicated. So then when you additionally consider that depending on the observation or the feedback that each of the agents get, then they have obviously a choice like what to do for each of these possible observations. You could in principle formulate a policy that, okay, I'm first going to take a particular action, and then if I receive some feedback, then conditional on that feedback, this is going to be my next action. You then basically have such a policy for each of the agents, and in principle, if you wanted to solve this very exactly, you should look at all of the possible combinations of all the policies for all the agents. So you really quickly get into this domain of exponential complexity that makes the problem really challenging computationally.
And do the agents communicate at all? Can they maybe share information? Is that within scope of the problem?
This is one of the factors that I wanted to specifically consider, because I think that a lot of the previous state-of-the-art work in information gathering for multi-agent teams, they tend to make this assumption that there is some communication during the task. So I wanted to see what I could do if I don't have this luxury of communicating during the task. What I decided to do is kind of split the task into 2 phases. So you have this kind of an offline phase that takes part before task execution, where kind of the agents are planning what they should do during the task. But once the task execution starts, so you deploy your robots or whatever your agents are, then you're not allowed to communicate anymore. So you have to kind of make plans beforehand and decide how you're going to act in each of the possible situations that arises.
Could we zoom in on an information gathering task? Are there real-world examples of where your sorts of research areas might be deployed for industrial or practical applications?
Maybe one of the kind of running examples that I've used in several of my papers is relating to search and rescue robotics. So you might want to deploy a team of robots to survey a disaster site and maybe locate some of the victims that might still be out there. So this would be one example of the potential application for my research work.
I think that's a great example in that when I think of a disaster area, I mean, it could be anywhere in theory, but I'm thinking of something like a search and rescue. There's not good Wi-Fi coverage, or there's environmental reasons where the agents cannot be centralized, or maybe centralization is too inefficient, that there's a lag or a latency in communicating. So I definitely see a need for a group of agents to coordinate, but without the need for communication. When you're deploying in a situation like that, is it similar to a single agent POMDP where I end up with a policy that's just kind of a finite state machine I should follow? Is that essentially what I get with your work in a DEC POMDP, that each agent is given this policy and they just go execute it?
In principle, yeah, that's exactly how it goes. As an end result of our optimization algorithm, we get one of these finite state controllers for each of the agents. And then they can take these and go out and run into the world and execute that policy.
Well, there's one topic maybe we should put a phrase on the wire, and it's the cursive dimensionality. I assume that kind of applies in this scenario. Do you look at it through that lens? And if so, could you maybe provide just a crude definition of the cursive dimensionality and how it applies in your work?
It's definitely a factor. So that's kind of one of the reasons for the computational complexity here, that you get into this massive domain of combinatorial explosion of the number of possible ways that you could combine policies or these finite state controllers for each of the agents. So for me personally, I actually don't have a formal background in computer science. So for me, first starting out in this problem, I didn't actually care so much about the computational complexity. I just found the whole approach kind of very appealing and somehow kind of intriguing, that we can actually solve such problems. It's kind of a fact in the background there that there is a reason for the complexity, but for me personally, it hasn't been kind of the main focus of what I do. I'm just kind of interested in, despite of this complexity, what can we do here and what can we achieve in such a problem?
Any complexity in exponential time is going to be pretty impractical for even small problems. Maybe some listeners are familiar with the Stewart and Russell textbook that covers not the decentralized version, but the single agent Lady and the Tiger problem, I guess it's called, which is also, exponential time and such a trivial case, but very complex to solve. It almost seems hopeless to think that we can apply some of these tools, but then, maybe there's a possibility of estimation or heuristics or something like that. Do you have any thoughts on how to make these theoretical frameworks more practical?
In the recent past, maybe 5 years or so, I think we have seen basically machine learning techniques generally make a strong appearance on the stage, and this is also happening in the domain of decision making. So there's kind of been a lot of renewed interest in applying reinforcement learning and also multi-agent reinforcement learning to kind of these complex decision-making problems. So I think that there are some exciting opportunities there that actually can help us to scale these methods to more complicated observational data or general kind of more realistic problems. So something that maybe still needs to be considered there is that then we typically, of course, also lose all these guarantees on the qualities of the policies and so on, and we lose the optimality. But I think that for now, it's great that we have these machine learning tools and we can kind of make progress. And I hope that the theory and kind of maybe also some more fundamental methods are going to catch up eventually. So one of the maybe differences that should be mentioned here between my work and this reinforcement learning work recently is that my work is so-called model-based or planning work. So I start with kind of a model of the problem in hand and then go and design policies. Whereas the approach in reinforcement learning typically is that you don't have a model of the problem, but you rather send the agents out to perform some trial and error and then learn from this experience. So there is a kind of conceptual difference, but I think they're kind of the two sides of the same coin. And I think there's a lot of possibilities that these two sides can also benefit from advances in one or the other.
Yeah, good point. When I started learning these things, I thought that they were kind of these polar opposites, but it actually seems there's a way they can collaborate, or the methodologies can, I guess. Maybe we can explore what it is about, if we describe, naively reinforcement learning as this basic from first principles, go ahead and learn everything. As you said, your approaches start from sort of an assumption of the model. I assume that follows some of the typical POMDP setup with a tuple where you have states, actions, observations, whatnot. Could you elaborate on what you mean by the model?
Yeah, so that's precisely what I mean by the model. So it's this tuple of the components. There is a state space. So this is the possible situations or things that might be of interest in the world that you want to model. Like, for example, where are the agents located? Where are the targets of interest? And so on. And the state is not observable to the agents directly, but they can rather perceive it through their sensors. So they get some partial and possibly noisy observations of the state. Besides this state space, you have, as mentioned, these observation spaces for each of the agents, and you have the action spaces for each of the agents that describe what the agents can actually do in the environment. And then, in addition, you have some kind of probabilistic models that actually model the effects of the actions. So on one hand, if the agents are going to take this set of actions in this particular state, then what's the probability distribution over the next state of the world? And then you have a similar kind of probabilistic model for the observations. Like, okay, if this is the state and the agents are taking these actions, then what's going to be the probability distribution over the observations that the agents are going to receive? So these kind of model the environment, the agents in it, and somehow the dynamics of the environment. And then finally, in addition to this, you have the reward function, which encodes the task of the agents. So this then specifies typically for each pair of states and actions the agents take, what is the numerical reward that they receive for taking this particular set of actions.
Those probabilistic components are very fascinating. Could you maybe contrast these approaches to an approach for something like the game of chess or Go?
Chess and Go are examples of games where the dynamics are deterministic. So if you're going to move your knight or your pawn in chess, then you can be fairly certain that it's going to move to the square that you wanted, or at least this is the assumption we make in computer chess. So the difference between these probabilistic models and these deterministic models is that you don't really have certainty over what the next state is going to be. So if you want to continue with the chess analogy, then maybe a probabilistic version of chess would mean that your pieces don't always land on the squares that you wanted them to, but maybe a little bit on the side some of the time, and so on. So you have kind of uncertainty about what's going to happen next.
Right. So I find myself kind of pretty intimidated at playing a game where I can't be sure the state of the board or that my actions are going to end up in their results. How is it possible that any practical result comes out of a framework like this?
The way to handle this typically is to work with expectations or expected values. So you want to kind of design policies or solutions in a way that in expectation they will lead to good results. So it doesn't mean that you can guarantee a good result, but in expectation you're going to do well. So this typically means that you have to account explicitly for these possibilities that things might not go as you maybe assume, but you have this distribution over the possible outcomes that might actually happen, and then you need to take action conditional on what you perceive.
So we're dealing with a class of problems that are harder than Go, which is exciting and intimidating. You'd mentioned the reward function, which I think is kind of the heart of all of these partially observable techniques, that the agent is aware that for certain states taking certain actions, they get certain rewards. Maybe could we give a practical example in like a search and rescue or one of these kinds of cases? What would a reward function look like?
The reward function is supposed to be something that encodes the task in a sense that if you take a useful action, you're going to get a high reward, and if you take a poor action, you're going to get a low reward. Or alternatively, you could model something like resource usage. So if you take an action that expends a lot of energy, like if you have a team of unmanned aerial vehicles, let's say in a search and rescue task, they decide to fly really fast over the area or take a long trajectory to get somewhere, then this is going to use a lot of energy. So this would be like a factor that diminishes the reward that you can expect to get. And on the other hand, then you have these things that if you achieve something like reach a goal, then you would typically want to associate this with a high reward. Like let's say this unmanned aerial vehicle reaching the desired goal, then this would be a positive thing that you would reward with a high positive reward.
In that regard, I think of both POMDPs and decentralized POMDPs as a framework. They tell you everything you need to know about the problem, but they don't necessarily impose the solution framework for you. Within that, though, we have to make some choices, like are we trying to maximize the average reward or the optimal reward within some discounting factor or maybe finite horizon? What are your approaches in figuring out how we utilize that reward function?
The primary distinction is that typically you are indeed concerned with your return over a long horizon of time. So you don't only care about the immediate reward that you're going to get, like after taking the next action, but you care about what consequences this action is going to have on my ability to get more rewards in the future. You want to kind of plan in a way that over a long horizon of time, you're going to be able to maximize your rewards. And the framework that I'm working with is the maximization of expected rewards over a finite horizon. So the finite horizon is chosen because we are dealing with information gathering tasks, as I mentioned, that have kind of a finite duration somehow naturally. So this means that if we are going to deploy a team of robots to get some information for us, then typically we want the robots to report back at some point in time. And this should not be an infinite amount of time, but rather a specified finite horizon of time. So that's why we look at rewards over some finite horizon of time. And specifically, we look at the expected sum of such rewards.
Makes sense. I mean, for me, there's no loss of generality because anything practical is going to be on some finite horizon. Does that give you any computational advantages by taking that path?
So let's say that there are maybe few compared to tackling the infinite horizon case. So at least you can kind of, in principle, you have the possibility to solve this problem exactly if you wanted to, if you have the computational capacity to do that. But in practical terms, it doesn't actually make that much of a difference. So it's still very demanding.
So in the framework, we have a multi-agent system, 2 or more agents going out, and presumably they're sort of collaborating, although I guess they could be adversarial in theory. But the DEC POMDP is going to look at I believe, the joint belief and the joint reward. Could you talk about the framework for moving from, a single agent having just their own beliefs about the world and the state and their own rewards, of course, to how you coordinate across the 2 or more members of your team, I guess, if you will?
Here, I think, is the main distinction between my research work and then, let's say, the single agent approaches. So in the single agent case with, let's say, something like the POMDP, typically what the agent is able to do is that it can track a so-called belief state, which is a probability distribution over the state. Given that the agent knows that which actions it took and which observations it perceived, and it knows the model of the environment, it's possible to apply a Bayes rule to actually track a probability distribution over the state. Now, when we move to the multi-agent case, of course, any individual agent is not aware of or cannot be certain what the other agents are doing, which actions they're taking, or what they're actually perceiving. And because these models in the DEC POMDP actually are kind of governing the entire system with all the agents, this means that an individual agent typically has insufficient information to track this belief state during execution of the task. It's just that the agent lacks the necessary information to do this. You don't have access to the observations of the other agents, and you don't know for sure what actions they have taken. So now I wanted to kind of see if we can somehow still formulate and solve a problem where the agents actually have this joint information gathering task, in the sense that once they are deployed and then report back after this finite horizon of time, then we can pool all the information the agents have, and then we can estimate this probability distribution over the state, or the so-called joint belief state. And joint, since it refers or uses information from all of the agents. So this is possible because we have the model of the system, and we have this first offline phase where we can kind of plan what each of the agents is going to do. So during this offline planning stage, we can use the model to kind of hypothesize what might happen if the agents decide to follow this particular set of policies. And we can see which one of these combinations of policies is going to lead into a favorable joint belief state. So which policy is expected to produce let's say, a belief state that has the lowest entropy, or in other words, the lowest uncertainty about the state of the world.
With regard to information gathering, is it worthwhile to compare and contrast your approach with something like FastSLAM, the Simultaneous Localization and Mapping algorithm?
It's certainly related. So simultaneous and localization and mapping is very popular in robotics, and the idea is to kind of estimate a joint probability distribution over some kind of map, and actually the location of the robot within that map. So I would say that the distinction is that in most SLAM algorithms, the idea is that you're just going to get some sensor data and then you're going to filter that with using the SLAM filter and update this probability distribution. In my work, I look at also the option that the agents actually can actively influence what kind of data they might get in the future. So you could think about this like as a robot that is not just going to passively filter all the data and use the SLAM algorithm, but rather the robot might think about it and decide to go left or right depending on where it believes it's going to actually gain most information about map or its own location.
And as we've discussed these techniques, well, in one sense, the fact that they're offline planning, as you said, means maybe we don't care too much about the complexity. If we can get an answer by investing a lot in compute power and perhaps it could be parallelized, we can get these nice policies and then deploy them in real time. But that assumes we can actually solve one of these exponential time problems, which might be impractical. So we need some sort of approximation, I guess. Could you talk a little bit about the way you've applied heuristics to move this from theoretical to practical?
Yeah, so the approach that we apply has kind of two main parts. So the first part is that we restrict actually the class of solutions that we consider. So this means that we are restricting the class of policies that we are considering as potential solutions to the problem. And the way we do is that we concentrate on finite state controllers. So these can be represented as kind of a graph where each of the nodes contains an action that the agent should take. And then there are edges leading out to other nodes that describe which is the next controller node conditional on the observation that the agent receives. So on one hand, we're doing this restriction of the space of solutions that we are searching in. And kind of the second part of the approach that we do is that instead of exhaustively searching through all the possible combinations of these finite state controllers, we kind of try to do local modifications to each of these controllers. So let's say that we have some initial set of controllers. In our case, we generate this randomly just to start with. So then we start to modify these controllers a little bit at a time. So we might say that, okay, let's try to change the action that the agent is going to take in this particular controller node. And then we see if this is going to improve the expected value or the expected return that we get in the end. And similarly, we might decide that, okay, let's change these edges. Let's make them connect to some other nodes. Maybe this is better for the overall solution quality than sticking with the current solution. So these are kind of the two main techniques that we use to make this somehow practical.
So would it be fair to characterize this more as a search than a calculation?
I think it is a search problem in essence. So we're searching in this space of possible combinations of controllers, and we're using somehow a very specific strategy of where we just locally modify these controllers. So of course, this means that we are not going to necessarily find an optimal solution to the problem. And the other hand, because of the way we do it, we are actually producing a heuristic solution, which means that we don't actually anymore have even guarantees on the quality of the solution. So we don't know how much worse than an optimal solution we are.
But at least you have a solution, right?
Indeed, yeah. And in practice, it worked quite well in many cases. So admittedly, we looked at rather small problems where even an optimal policy is not super complicated, but our approach was able to find optimal policies actually in several of these cases. So at least practically, it seemed to work nicely in these problems.
Could we explore some of your experimental results? I know you compared your approach to some of the existing things in the published literature. How do things stack up?
Before we started with this work, there actually wasn't any existing algorithm that could directly tackle the problem that we were interested in. So the reason for this was the fact that we wanted to look at these information gathering problems, where actually the reward depends somehow on the knowledge that the agents have. So the typical case with existing algorithms is that you want to directly optimize over, let's say, reaching some goal state or something similar, where you can just state the objective as a function of the state in the system. So in our case, the objective is more like a function of what the agents know about the state. So we were able to adapt a few of the existing DEC-POMDP planning algorithms to kind of apply to our problem setting as well. So these were typically some either like brute force algorithms that find the optimal solution, but they don't scale up, or then some more advanced heuristic search algorithms, but that were still designed for this goal achievement type of task. Basically, given kind of this background, it's not extremely surprising that we were able to actually outperform these other algorithms. So, but that I think it mainly kind of is because we are actually targeting a slightly different problem than what is done in the usual state of the art.
And you had mentioned part of the work is restricting that class of policies to only finite state machines. I guess one criticism could be, well, a finite state machine has limited capabilities. It's not a Turing machine, not even a push-down automata. There are other models of computation that, in some sense more powerful. Is there a loss of generality in any way by assuming you're going to only look at finite state policies?
In principle, this doesn't mean that we are losing generality. So the reason is that in a DEC-POMDP, the most general policy description that you could have is kind of a tree, basically a decision tree that kind of specifies the actions to take and then conditional on all possible next observations, what again the next action is, and so on. You have one of these for each agent. And in principle, if you work with finite state controllers, then you could, in theory, just increase the size of this finite state controller to be large enough that you can actually represent this tree type of policy. So in this sense, we are not losing generality here.
Makes sense, yeah. You just have to pick the right horizon, I guess.
Yeah, the right horizon, and you want to have kind of the controller large enough and then still hope that you can actually practically compute the solution.
Could we do a little bit of a deep dive on the algorithm itself? I think referring people to the pseudocode in the paper is ultimately the authoritative source, but in broad strokes, how do you go about doing that search?
In very broad terms, this algorithm has kind of two main phases. So first of all, we have this so-called forward pass, should not be confused with what is typically meant by a forward pass in artificial neural networks. This is something slightly different. But the idea in this forward pass is that we are now taking our current finite state controllers for each of the agents, and we're kind of doing this simulation of, okay, what might be the possible joint belief states that we actually reach by following this set of policies. So this gives us kind of, for each of the controller nodes that we have, somehow a set of possible joint belief states which could be reached in this particular node. So we kind of do this computation once, and then we store these results. So then the second main phase of the algorithm is the so-called backward pass or backward phase. Here we are doing these local modifications of these finite state controllers. So what we're actually doing is that we are looping over all of the nodes of the finite state controller of a particular agent, and we are taking these results from the forward pass and seeing, okay, if we're now optimizing this particular node, what are the possible joint belief states that we could reach in this node? So then we try to reason about changing, on one hand, the action that the agent is going to take in this controller node, and on the other hand, what are going to be the next nodes conditional on the observations. And we kind of solve a large optimization problem, maximizing the expected future returns over all these possible configurations of this particular finite state controller node. And as a result, we kind of find somehow a local best response policy that what should this agent do if it is now in this node and the other agents are following their current finite state controller policies.
Under your framework, do the agents in the multi-agent system all follow the same policy, or are you customizing them to each robot or agent or whatever?
In our scenario, each of the agents is following their own policy. There is diversity in that sense.
And does that derive from qualities of the agent themselves, or is there something that might make specializations within how you want to deploy the agents?
This is a question that's largely task dependent. So let's say that if you have a team of agents or robots that have essentially the same capabilities, then it might actually make sense that you are optimizing a single policy that all of them are going to share. Since all of them are going to be able to solve the same tasks, they're going to be able to take the same actions, they have the same sensors and so on. So in this case, it could make sense to actually share the policy between the agents. Of course, in like the general case, you might have a heterogeneous team where each of the agents has unique capabilities. So it might not be possible even to directly apply the policy of one agent to another. So this is something that depends on the task. And we looked at the case where all the policies were different. So the case of heterogeneous agents.
I was wondering if you could compare and contrast your approach to some of the other multi-agent approaches you might be familiar with. For example, I've seen decentralized POMDP approaches that lean heavily into game theoretic solutions. I also know the interactive POMDP or iPOMDP fairly well. Shout out to my old advisor who worked on that. Do you have any, general thoughts on where your framework fits into the overall scheme of different POMDP varieties that are out there for multi-agent systems?
I think that DEC-POMDP in general, it subsumes actually a large class of these POMDP or MDP variants. So kind of if you restrict a DEC POMDP to a single agent, then what you're going to get is actually the POMDP. And then again, if you restrict further the observation function, so in the sense that the agent can perceive the state completely, then what you get is an MDP. So there's kind of this hierarchy of problems that you have. And somehow the DEC POMDP is probably the most general cooperative MDP flavor. Of course, then if you go beyond the cooperative scenario, you get into this game theoretic setting. So then you run into partially observable stochastic games, which you could argue are still like a generalization of DEC POMDPs, where each of the agents has its own individual reward function that they're trying to optimize for.
And I'm curious, where has this research led you next? I know this was published a little bit ago. It's still recent, though. What have you worked on since, and maybe what are you excited about for the future?
This paper was a couple of years back, and since then I've kind of thought further about this framework, and somehow the most exciting recent result that we have is that actually this setting of information gathering and this, let's say, classical setting of trying to achieve a goal, they're not as kind of disjoint as I believed maybe a couple of years ago. So recently we have been able to show that if you kind of modify this so-called classical goal achievement problem by adding what we call prediction actions, which are essentially actions whereby the agents are kind of making a declaration about the state or voting about what they think the state is, then you can actually kind of unify these two approaches. So what I find exciting about that is that now we can connect this problem of decentralized information gathering to all of the theory that we have for, let's say, the standard DEC POMDPs. So we have kind of made this connection, and this means also that now we can apply tools like multi-agent reinforcement learning, which typically takes as starting point the standard decentralized POMDP. So now we could conceivably at least apply reinforcement learning methods to these information gathering problems. This is what I find really exciting, and I hope to also contribute to that in the future.
All right, well then to wrap up, where can people follow you online?
You can follow me on Twitter. My handle is Mikko_Lauri, so my first name _ last name. And I also have a personal homepage where I talk more about my research, so that you can find at laurimi, so laurimi.github.io.
Excellent. I'll have links to both of those in the show notes. Well, Mikko, thank you so much for coming on to discuss your research and your expertise. This is really interesting.
Thank you for having me.
That concludes this installment of Data Skeptic Consensus. Our guest today was Mikko Lauri. Claudia Armbruster is our associate producer, Vanessa Burciaga does guest coordination, and I've been your host, Kyle Polich.